So this is lesson number 3 in this series on nonlinear systems. In the last session, we had a look at some of the examples related to nonlinear systems, and we saw how the behavior of a nonlinear system is different from that of a linear time invariant system. Now we'll be studying today types of nonlinear systems, and we'll be looking at different types of nonlinear systems and some commonly occurring nonlinear systems. So first of all, the types of nonlinear systems. So we can classify nonlinear systems into we have a number of ways of classification methods. First, we'll classify them as inherent or induced nonlinearity. So a nonlinear system can be classified as a inherent nonlinearity or an induced nonlinearity. So it's quite evident. Inherent nonlinearities will include all those types of nonlinearities that are actually present in the system by default, and they are not induced in the system, while as there are certain other systems which do not have nonlinearities as such, but nonlinearities are induced in those systems for different purposes, for various applications. And in the case of inherent nonlinearities, you have, like, say for example, saturation, you have hysteresis, and extra. For induced nonlinearities, you have something like a relay. A relay is not naturally occurring system, but it is something that has been designed specifically to make sure a system trips fine, a relay operation. So you have different types of nonlinearities, and one of the classifications of nonlinearities is as inherent or induced nonlinearity. Second type of classification of nonlinearity includes magnitude or frequency based nonlinearity. So magnitude based nonlinearities, where the nonlinear behavior stresses on the magnitude of the output, is known as magnitude based nonlinearity, while as in other types of nonlinearities, the nonlinearity is basically induced in the frequency response of the output, and from there we can actually say that this is a nonlinear system. So again, if you have a look at this magnitude based nonlinearity, something like a saturation nonlinearity is a magnitude nonlinearity. We understand with the saturation what happens is that after a certain period or a certain range, output of the device does not increase further. Even if we increase the input, the output saturates and output will not change, it becomes constant. So there is a magnitude involvement in this case. while as in frequency nonlinearities, again you have an idea about this through harmonics. We know harmonics are actually induced in a system because of some nonlinear device, and that actually features through the frequency as a frequency based uh, response in the output. And we know harmonics are basically multiples of the fundamental frequency component, so uh, they are these types of nonlinearities are visible in the system in the form of frequency. They will actually modify the frequency of the system. So you have magnitude based nonlinearities that actually fundamentally uh, cause a change in the magnitude of the output, whereas you have frequency based nonlinearities that actually cause a change in the frequency of the output. The third and one of the most important classifications of uh, nonlinear systems is hard and soft nonlinearities. So as far as hard nonlinearities go, these are those systems, those type of nonlinear responses that cannot be linearized. Whereas soft nonlinearities are those types of uh, nonlinear responses that can be linearized. So there are some nonlinear systems in which we can apply linearization approximation, and through linearization we will be able to convert the nonlinear dynamic equation into a linear dynamic equation, and thereafter go for analysis and controller design. But there are other types of nonlinearities that are actually hard nonlinearities. They cannot be linearized, and because of that behavior, it is not possible uh, for us to linear to analyze them in linear domain. So such type of nonlinearities have to be dealt directly in the nonlinear domain itself. So looking at the examples of hard and soft nonlinearities. In hard you have something like backlash or bang bang relay, fine. And soft nonlinearities, like say for example we derived the motion of a simple pendulum uh, in the last lecture. So that type of nonlinearity can be linearized, and we'll be seeing how we can linearize such systems, and through that linearization we can analyze and design a controller for a simple pendulum. Fine. So these are types of nonlinearities that based upon different properties, based upon different characteristics of nonlinear systems. So we can classify them into these three different groups, and you can have different other classifications, but these are some commonly occurring classifications. And among these, what we are going to be focusing on is the hard and soft nonlinearities. Now moving on, now we'll be studying some commonly occurring nonlinearities in nature, and these nonlinearities are we can actually see these non-linearities in almost every system around us, and therefore the studying these non-linearities is very important. So the first one that will be looking at is a saturation nonlinearity. So we understand what a saturation nonlinearity looks like. So we'll be so this is a saturation nonlinearity here. So you can see if this is your output and this is time or input, whatever be the case here. So you can see what happens here is after a certain period of time or after a certain input range, the output does not change with respect to either the time or the input any longer, and the output saturates. Fine. So this I've shown a very fast transition from linear to from a linear variation to constant. So it can be actually uh, something like this that we see in case of, like, say for example, magnetic saturation. After a certain we can increase the field current, but after some time the flux will vary with it, but after some time, you'll see that even after increasing the field current, the flux will not change. So this behavior may not be as fast. जो transition मैंने यहाँ पे दिखाया, the transition from linear domain to constant will not be as quick, but this is what saturation looks like. So also it can take it as is shown here. It can be the saturation can occur only in the first quadrant, or it can also for the same system occur in the third quadrant as well. Fine. So regarding this, it is one of the most common type of behavior that we see, and the examples of which you see in case of machines, you see electromechanical devices, fine, in actuators, in amplifiers, extra. So also this is inherent non-linearity, and most of the times it's actually inherent, and in very few cases we induce this in a system. Second one is a dead zone. So in this case, the behavior, the output response is something like this. So this is how the output will vary. Fine. So here you can see in case of dead zone nonlinearity, what happens is that the output response uh, for a certain period of time, so for a certain range, the output does not vary with respect to the input or time, and the output is actually zero, and after only certain uh, gap, the output responds to the change in input. So this type of response again you have seen in a number of nonlinear devices. Say for example, in case of diodes, in case of SCRs. So there are intervals where the output will not vary with respect to input, and only after uh, some particular range, after some input value only, the output will change with respect to the input. So examples of this include sensors, again amplifiers, and you can say semiconductor switches, extra. Fine. Third type of nonlinearity that we can that we see is the backlash nonlinearity. The output response of this is like this. The word of just do not mix this with hysteresis response. So this is how a backlash nonlinearity will look like. It will be actually centered around the origin. So the output in this case, so this is your output with respect to time t. So as you can see, what happens here is output does not initially change with respect to time t for a certain period of time, then it starts to increase. Of now if we decrease back the input, this is your time or input, so if we decrease the input, so we are expecting the same behavior that we had experienced in the forward motion, but that does not happen. The system will, the output will not change at all with respect to the input or time for a certain period, and then start to decrease. So now we look at backlash. Now we look at first hysteresis. That will be the fourth type of nonlinearity. So this is the hysteresis behavior. So what happens here is the input will and the output will change after with respect to the input value, and then if we decrease the input, it will not retrace the path, it will decrease but to a different path, and then same will happen when we increase it again. So it will not retrace the same forward path in the once we retrace the input value. So this is different from backlash because there is no period of time where the output will be constant with respect to the input, but in this case, in case of a backlash, the output remains constant with respect to the input value. So backlash, where we actually find this is gear mechanism. So mechanical gears. Fine. So you might have you have a might have two interlocked devices like this. What happens is, in this case, since the two these discs are locked with each other and they are rotating, so for some interval of time during the motion of this upper gear in the lower upper slot in the lower teeth of the lowered gear, fine, what happens is that during the motion in between the teeth and the slot, there will be no change in the output with respect to the input. Only after the teeth traverses the path in the slot, there will be a change in the output with respect to the input. So during that period of motion, during which the teeth is actually rotating in the slot, there will be no change. So this is seen in case of gear mechanisms. Fine. So this is again you see in a clock. Say for example, the minute hand will not. There will be clocks where the minute hand does not change as for. It will only move from one digit to another only after the complete traversal of 60 seconds by the second hand. Fine, the minute hand will not change. Similarly, the hour hand will not change. So this is something. These gears you see, uh, we see in case of clocks, we see in case of many mechanical devices, and the output will not change with respect to the input as long as the gear is traversing this path. The teeth of one gear is traversing the path of the slot in of the another gear. While as in case of hysteresis, there is a continuous change of output with respect to the input. There is no period of time, no range of input for which the output will remain constant, and therefore, and this phenomenon we see again in case of machines and electromagnetic devices. We see how a hysteresis loop occurs and how it causes hysteresis losses in electrical machines. Fifth type of nonlinear behavior is Coulomb friction. We have studied about viscous friction in linear systems. Say for example, in case of both, we have seen in a number of electromechanical devices like in electrical machines, and we saw that equation of motion of tau equal to j d omega by dt plus b omega. So that b there was actually viscous friction coefficient. So that equation actually represents a linear behavior. But as far as the Coulomb friction is concerned, Coulomb friction represents a non-linear behavior. Viscous friction, in case of viscous friction, you see that the output is proportional to Bu, Bv, whatever. And while as in case of Coulomb friction, what happens is that the output is proportional to, I'll write C for Coulomb friction, Cu square. So it's actually proportional to the velocity square. Tau is equal to J d omega by dt plus b omega. So tau is proportional to b omega. So if we say the output is tau here, so it's proportional to b omega. Similarly, we see in case of a spring, we can introduce a mass spring damper system. We see that there is equation of motion again involves bx dot. Fine. So viscous friction represents that frictional coefficient wherein the output is proportional to the velocity of the motion. But while as Coulomb friction is actually represents that friction wherein the coefficient of friction is actually proportional. It causes the output to vary with respect to the square of the velocity. It is proportional to the square of the velocity. Since this is proportional to the square of the velocity, this causes a non-linear behavior. So this Coulomb friction here represents a non-linear behavior in all systems. So 6 now, you have on-off nonlinearity. On-off nonlinearity or relay or bang-bang, so it goes by different names. And what happens in this case, or it's a simple switch, on-off nonlinearity, a relay, a bang-bang controller, so sliding mode controller, signal function. So all these represent have a characteristics like this, wherein the output is +1 for all inputs, for all positive inputs, and it's equal to -1 for all negative inputs. And such type of nonlinearities are not inherent in nature, but they are induced in a system. And the purpose of inducing these nonlinearities may be, in case of relays, for simply tripping the device; in case of sliding mode controllers, for controlling the output of the device; and again, with the bang-bang controller, we are able to control the output of a system. So the purpose of using this nonlinearity is for control, for protection, extra, and it's not inherent in nature, it is actually induced in a system. This behavior again represents a nonlinear behavior. So these are the commonly occurring nonlinearities that we'll be encountering. And seventh, you can have a combination of these nonlinearities. For example, saturation and dead zone. So saturation and dead zone, it will look something like this. So this here represents your dead zone, then this was your output, then it can be saturated as well. So these are you can now have a combination of these nonlinearities occurring in many systems, and you can have a dead zone with a hysteresis. You can have a dead zone with on-off nonlinearity. You can have a dead zone with backlash. So these combinations can be also found in different types of nonlinear devices. And these nonlinearities, we have not gone into the mathematical modeling of these nonlinearities as yet. After we take up the describing function method, we'll be analyzing these nonlinear systems, these nonlinear behaviors for their mathematical models, and we'll be trying to derive the mathematical model of all of these systems, all of these nonlinear devices, be it the hysteresis nonlinearity, the saturation nonlinearity, the dead zone nonlinearity. Using a describing function method, we'll be trying to find out the mathematical model of all of these nonlinear behaviors, and through that we'll be able to analyze the system behavior. So today we have only seen the behavior of nonlinear systems through their output characteristics, their VI, their XY plots, and through that you should be also able to analyze system for whether it is a linear system or a nonlinear system. For example, this type of behavior we know represents a linear system. Now, whether this type of system is also linear or non-linear, that you have to understand. So why shifting this output response from the origin will make this a linear device or a non-linear device. Fine. So this property here is something that we see in case of backlash non-linearity. So this is actually a curve representing the behavior output behavior of a system varying with respect to input, and only one we are only focusing on one path of a backlash nonlinearity. So this system here is not a linear behavior, but it is a non-linear behavior. This is a behavior of a non-linear system, not that of a linear system. So we need to understand these things. We need to understand, looking at the characteristics of certain systems, whether or not these are linear devices or non-linear devices, whether or not this is a linear behavior or a non-linear behavior. So there will be systems where there will be linearity present, but we are looking at, as I said to you in the first session itself, we'll be considering all those systems non-linear that do not have sufficient linearity. Even if there is a hint of non-linearity present in that system, we'll say that we'll take it as a non-linear system here. So this second curve here represents the behavior of a non-linear system, not that of a linear system. Even if the output is varying linearly with respect to the input, because of that shift in the origin point, this becomes a part of a backlash nonlinearity, and there is a hint of nonlinearity in this system that is enough for us to classify this as a characteristic of a nonlinear system. That is all for today. So we have looked at different types of nonlinearities and some commonly occurring nonlinearities. We have yet to derive the mathematical model of these commonly occurring nonlinearities. We will do that only after we take up the describing function method, and only after that we'll be analyzing these nonlinear behaviors. Fine. So this, for now, you have to only remember the characteristics, the output behavior of these systems with respect to input, with respect to the time. So that's all for the session.